Now let's look at the first example problem illustrating the technique of meet in the middle. So this is a LeetCode problem called the 4-sum 2. So we are given 4 lists of integer values, and we are asked to compute how many tuples I, j, k, l, which are indices into the 4 list, so that the sum of the corresponding element is 0. So in this case, all the arrays have the same length, and which is at most 500, and all the integers are in this range, so that adding 4 will not overflow a int. So here, let's look at the example. Suppose we are given this 4 list or arrays, and the answer is 2 because there are 2 ways to make 0 by picking one negative 2, one negative that give us -1, so we need another one. No, actually, yeah, so we can pick a -1 and 2, so that give us a 1. So that's the only way to get a 1 from CD. If we pick 1 and -1, we get a 0. So then we want to get a 0 from picking an element here and element here, and there's no way to do that. So if we pick 2, -2, that also gives us 0, and that wouldn't work. And if we pick 2, -1, that gives us 1. So we need a -1 from these two. So -1 and 0 would do. So these are the only 2 ways, the only ways to make 0. So then how do we solve this problem? So obviously a brute force approach would be n to the power of 4 by traversing over all possible indices combinations and check their values. So that's not going to be efficient enough. So how can we improve that? So we can do it in n cube time by using the idea that we used earlier for solving 3-sum or even for solving 2-sum. So essentially, if we iterate over all combinations of A and B, an element in A and element in B, then we need to find 2 numbers here from C and D that sum up to a particular target. So that's basically 2-sum. So after we fix the value in A and fix value in B, we just need to solve a 2-sum problem. In the 2-sum are in the 2 array, but it's the same concept. We just need to sort both array and then use 2 pointers. So that's because the 2 pointer part is order n, and enumerating through A and B, that's n squared. So all over this is n cube. So we can solve it in cube time without any extra memory. So we're not using extra storage. We're just sorting C and D, which can be done without using extra memory also. So what can we do faster? Can we get this down to, say, n squared time? And the answer is yes, but in order to do that, we have to pay memory overhead. We have to store results. So there are different ways to do it. So in fact, our discussion using this example kind of illustrate the technique. So suppose we first loop through everything in A and B, and then we just store that result. So we can store them in different ways, but one of them ways is we store them in a sorted array. So that will be, they're at most n squared, so we store that in order n squared. And this takes n squared time. And then we do the same thing for C and D, all combination of C and D, and then we store that. So that also takes n squared time. So here we have n squared plus n squared, which is still big O n squared. Now we have 2 sorted array. Each of them have at most n squared. Then we can use 2 pointers to find out whether we can construct a 0 in them. So The interesting about this for sum is this a k sum problem where k can range from 2, 3, 4, 5, 6. There are many ways to do it, so it's not that is only one way. Another way is instead of storing going through both parts and store them in a array, we can going through, let's say we go through C and D, and then because here we want exact match, we want this to be 0, we can actually use a hash map which store the for each value how many indices can, how many pairs of value from C and D can get that value. Then once we computed that, the hash map, then we just need to go through every element in A and every in B, that's n square, and then we just do a hash lookup. So because giving a value here, giving a value here, we know what value we need in order to reach 0. So that's pretty much it for these problems. Yeah, so we can do n cube by sorting without using actual memory. To get n square, we use actual memory. And this is meet in the middle because we sort of computed half, the two array of the 4, half of it, and then we pre-compute the result and store it. Then we can also pre-compute the other half, and then we're just trying to comparing the intermediate result. So this is kind of a meet in the middle. So this is my code in Java. So given A, B, C, D, I use a hash map which store all the intermediate result from A, B. So this is map each number to the number of ways to get it. So just loop through all elements in A, all elements in B, and then use this merge thing to add 1 to the value corresponding to the key x plus y. And then we just loop through everything in C, everything in D. And now, given the sum x plus y, we are looking for negative x plus y. So if it doesn't exist, then that's 0. So if it exists, we get how many count it is, and then we just add it. So very simple logic here. So to summarize, if we look at two-sum, we can define the problem as either wanting exact sum or wanting near sum. So wanting near sum is strictly harder because if you compute the near sum and it turns out to be the same as the exact sum, then you know it is exact sum. If it's different, then you know there isn't exact sum. So if you solve near sum, you also solve the exact sum. So for exact sum, for two sum, we can use a big O n time, but we need a big O n memory. So this is basically using hash set. For near sum, this hash set doesn't work because we're not just looking for one value. We need to keep track. So then the method is we need to first sort the array, and then we use 2 pointers to solve it. The same method can also solve two sum. So in practice, this would be faster than the exact sum, than using hash set. For three sum, the exact sum, the best method turns out to be the same as the one for near sum, or at least there might be other method, but what I can come up in mind, I guess without too much thinking, is just do it in this near sum approach. We sort to array, and then we iterate over the third, and then we just do 2 pointer over the two sorted array. Because once we fix the element from the third array, we know what we want from the other two array. And for four sum, we can do it in So the problem we just did is exact sum. So we use this. We use big O n squared memory by storing this hash map, and then we need the big O n squared time. So big O n squared time for creating this intermediate data, but then after it is another big O n squared time for looping over all possible value and then do a lookup in the hash map. So this is yeah. So n squared plus n squared still n squared. If we want to solve near sum, then we need to sort. So I guess so we can either pre-compute the sum for. So yeah. So actually, I guess there are two different ways to do it. One is we pre-compute the sum of all elements in AB and also the sum of all elements in CD, and then we do 2 pointers. Another is we only pre-compute the sum of all elements in say C and D. Then for every, and then we sort that array, and then for every element in A and every element in B, once we know a target, we are trying to find the target in a sorted array. We can use binary search. So we only need to store half of the partial result, and then we use binary search to so that's also big O n square n square log n time. So one of the homework problem uses asks you to do 5 sum, and the thing I want to say is there are lots of flexibilities. So you can store 2 arrays, so sort of n squared 2 array. You can store another 2 square n array, and then you can loop over the third, or you can just store 2 array and then you loop over three of them. So I think the problem parameter is so that any of those approach implement correctly should be able to pass. And it's interesting to know in general, if you want to solve k sum, the time complexity is I think it's k plus 1 over 2. But then depending on whether k is odd or even, there's and sometimes you need to pay certain amount of extra storage.